Hello, I am Dorel Fetcu. I work at the Technical University of Iași in Romania, and this is my talk for the autumn edition of Geometric Analysis Past, Present, and Future. I want to thank the organizers for giving me this opportunity, and now I will begin my presentation. The title of the talk is Simon's Type Formulas for Surfaces in Solve and Applications. The purpose of this talk is to present, in the end, some new results about Simon's type formulas and their use in this very particular space, the solve space. But before arriving to this part of the talk, I will first recall some things about the history of using Simon's type formulas to describe the geometric properties of submanifolds. I will begin with the first paper by James Simons from 1968, and then I'll just point out some of the first and most important results obtained by using the kind of formulas that interest this talk. I will end this first part of the talk with some more or less recent results from 2011 up to 2017 that shows how Simon's type formulas can be rethought and how they can be used in order to obtain not only gap or rigidity results, but also compactness results, for example. Then I will say a few things about the geometry of the solve space, and I'll also recall some results, some important results on surfaces in this space, especially on closed surfaces, closed CMC surfaces, but not only that, also about totally umbilical surfaces and constant angle ones. Finally, the last part of the talk is about these new Simon's type formulas in the solve space, and I will present two new formulas of this type and also some pretty straightforward applications of these formulas. These applications are gap and non-existence results for closed CMC surfaces in solve. So let me first say a few basic things about constant mean curvature and parallel mean curvature submanifolds. So we consider M a submanifold in Riemannian manifold N, and we have the well-known Gauss equation that defines the second fundamental form of the surface, the induced connection on the surface on the submanifold. Sorry, and we also have the Weingarten equation, which defines the shape operator in a normal direction and the connection in the normal bundle. The mean curvature vector field of the submanifold is the trace of the second fundamental form divided by the dimension of the submanifold, and if this vector field is parallel in the normal bundle, then M is called a parallel mean curvature submanifold, or a PMC submanifold on short. And if the norm of this vector field, the mean curvature, is constant, then M is called a constant mean curvature submanifold, or a CMC submanifold. In 1968, James Simons computed the Laplacian of the squared norm of the second fundamental form for a minimal submanifold of a Riemannian manifold. And in the simpler case of the minimal hypersurfaces in the Euclidean sphere, this formula has this very nice form. Using the general Simon's formula for submanifolds in the Euclidean sphere, for minimal submanifolds in the Euclidean sphere, James Simons obtained a very important rigidity result. So first, integrating this formula over the submanifold, we get this integral inequality, and then as a direct consequence, one obtained this corollary saying that if M is a closed minimal submanifold in the Euclidean sphere, with the squared norm of the second fundamental form satisfying this inequality, where here in the right hand side we have a constant depending only on the dimension of the submanifold and the dimension of the ambient space, then either M is a totally geodesic submanifold or the squared norm of the second fundamental form is actually equal to this constant. So in the same time, we have rigidity and gap result for such submanifolds. This was the first result of this type in a very long line of similar important results. Thus, in 1969, Nomizu and Smith computed the Laplacian of the squared norm of the second fundamental form of a CMC hypersurface in a space form. And then in 1971, Erbacher, and in 1973 again Smith, found similar formulas for any PMC submanifolds M in a space form. In this case of PMC submanifolds, one computed the Laplacian of the squared norm of the shape operator considered in the direction of the mean curvature vector field instead of the second fundamental form. So I'll only present here the formula from 1971 obtained by Erbacher for the Laplacian of the squared norm of the second fundamental form. As you can see, the formula is more complicated than in the case of hypersurfaces studied by Simons, but it's still a very nice formula and it has a lot of interesting applications. Of course, at the beginning, these formulas were used in order to get rigidity results for CMC and PMC submanifolds in space forms. And as an example, I'll recall this theorem by Smith from 1973 that says that if M is a compact PMC submanifold of the Euclidean space with non-negative sectional curvature, then M has to be a product of minimal submanifolds of Euclidean spheres. Then in 1977, Cheng and Yao proved the very general Simons type formula for Kodazzi tensors. These tensors are symmetric 1-1 tensors defined on a Riemannian manifold and satisfying the classical Kodazzi condition. The formula reads like this. It involves the Hessian of the trace of the tensor S, the curvature of the manifold, and the eigenvalues of the considered Kodazzi tensor. It is easy to see that if we take, instead of the general Kodazzi tensor S, the second fundamental form or the shape operator of a submanifold in a Riemannian manifold, one recovers the Nomizu and Smith result and also the original result of Simons after we rewrite the last term in the Cheng-Yao formula. Problem is in other spaces that when the ambient space ceases to be a space form, then the shape operator or the second fundamental form of a submanifold is not necessarily a Kodazzi tensor. So the formulas will be more complicated, and the computations will also be more complicated. We don't have to look very far from space forms in order to have such a case, because when we work in product spaces obtained as the direct product between a non-flat space form and R, we already can see that for a PMC submanifold, the shape operator is not a Kodazzi tensor. Even in this setting, one can obtain Simon's type formulas, and useful one at that. For example, we have this theorem from obtained by Battista in 2011 in the case when the space form in this product space has dimension 2, and in 2014 for the general case when the dimension of the space form can have any value. So if sigma is a non-minimal PMC surface in product space, and we consider the traceless part of the shape operator in the direction of the mean curvature vector field, we have this formula for the Laplacian of the squared norm of this traceless part of A, where we use this notation. We have C, the unit vector field tangent to R, and T and N are the tangent and normal parts of this unit vector field. So the formula is complicated, but it still can be used in order to obtain rigidity results, as showed by this theorem, still from the same paper from 2011, paper of Battista. So if sigma is an oriented complete CMC surface in H2 cross R, satisfying these two conditions, then the surface has to be a vertical plane obtained as the product between a geodesic in H2 and R. In 2014, we obtained some similar results for surfaces in H3 cross R and S3 cross R. So our results read like this. If sigma is a complete non-minimal PMC surface in H3 cross R, satisfying two conditions quite similar to those imposed by Battista in the case of CMC surfaces in H2 cross R and S2 cross R, then either the traceless part of the second fundamental form has to be equal to 0, or our surface is a round sphere in H3. And the similar result in S2 cross R, still complete non-minimal PMC surface, satisfying two conditions of this type, and then the surface lies in S3, and either the traceless part of the second fundamental form is equal to 0 and sigma is a round sphere, or the squared norm of the traceless part of sigma has this constant value, and sigma is a torus. Then, in order to avoid working with formulas of this complexity, one can think about using another Kodazzi tensor instead of the shape operator or the second fundamental form. So in order to find such a nice tensor, such a Kodazzi tensor, we have to recall some things about the Abresh-Rosenberg differential. In 2004, Uwe Abresh and Harold Rosenberg introduced a holomorphic differential defined on CMC surfaces in product spaces M2 cross R. And their result was extended to any codimension by Alencardo, Carmo, and Tribuzzi in 2010. So the theorem obtained in 2004 and then extended in 2010 says that the 2-0 part of the quadratic form Q defined on a PMC surface in a product space by this formula is holomorphic. In the case when n is equal to 2, we have the Abresch-Rosenberg differential, and we will still call this differential Abresch-Rosenberg differential when the dimension is greater than when the dimension of the space form is greater than 2. So in 2011, Marcio Battista considered an operator S on a non-minimal PMC surface given by this formula. One can see that S is defined with respect to the quadratic form Q. And this operator has two very important properties. It is a Kodazzi tensor, and it vanishes if and only if the Abresch-Rosenberg differential vanishes. So using these two properties, Battista and then Rosenberg and myself obtained this nice formula, this nice Simon's type formula for non-minimal PMC surfaces in product spaces. So if sigma is a non-minimal PMC surface in a product space, then the Laplacian of the squared norm of S has this very simple form where K is the Gaussian curvature of the surface. This formula it's very easily obtained from the general chain-Gauss formula for the Kodazzi tensors. As applications of this formula, I'll still mention some rigidity results obtained by Battista in the same paper from 2011. So if sigma is a CMC surface in S2 cross R with the mean curvature greater than 1/2 and satisfying one of these two sets of conditions, so either it is complete and the supremum of the norm of S is less than C, or closed and the norm of S is less than C, where C is a real constant depending only on the mean curvature, then sigma is an embedded rotationally invariant CMC sphere, one of the four surfaces described by Abresch and Rosenberg in their paper from 2004. Then another theorem of this type, this time in H2 cross R. So if sigma is a CMC surface in H2 cross R with the mean curvature greater than square root of 5/2, and the surface satisfies some similar properties to those in the previous theorem, then sigma again has to be an embedded rotationally invariant CMC sphere. The formula of the Simon's type that I mentioned before allowed us to extend the very nice theorem by Alencardo, Carmo, and Tribuzzi to the case when the sectional curvature of the space form considered in the product space is greater than 0. So originally this theorem was proved by Alencardo, Carmo, and Tribuzzi in 2010 only for negative values of the sectional curvature C, and by using the Simon's type formula it's quite easy to extend the theorem for all sectional curvatures different from 0. So we have this theorem that says that if sigma is a complete non-minimal PMC surface with Gaussian curvature non-negative, then one of the following holds: either the surface is flat, or it is a minimal surface of a totally umbilical hypersurface of the space form, or it is a CMC surface in a three-dimensional totally umbilical submanifold of the space form, or it lies in M4 cross R, viewed as submanifold in R6 endowed with Lorentz metric, and it can be described in the terms of the existence of a plane such that the level lines of the height function are curves lying in planes parallel to this plane. As I said, the theorem was proved for C less than 0 by Alencardo, Carmo, and Tribuzzi, and they also described the surfaces in the fourth case. Our contribution is only related to the extension of the theorem via Simon's type formula for C greater than 0. As I said in the beginning, Simon's type formulas cannot be used only for getting rigidity and results or gap theorems. It is possible to use it in order to obtain other type of results. For example, compactness results. So to illustrate this idea, I chose two theorems obtained in 2017. The first one says that if sigma is a complete CMC surface in a product space M2 cross R, such that the integral of the squared norm of S is less than infinity, then provided that the mean curvature satisfies some inequalities, depending on how the sectional curvature of the space form is greater or less than 0, then sigma has to be compact. And we have another result here that also involves the normal part of the unit vector tangent to R. The second result says that if sigma is a complete CMC surface in M2 cross R and C is less than 0, then if the mean curvature satisfies this inequality and the integral of the squared norm of S plus the squared norm of N, the normal part of C, is less than infinity, then again the surface has to be compact. Now I'd like to say a few words about the space Sol. This is the Lie group Sol. It actually is R3 endowed with a Riemannian metric given by this formula, where X, Y, and Z are the usual coordinates on R3. We can define a left invariant orthonormal frame field by these formulas, which is called the canonical frame. And with respect to this canonical frame, the Levi-Civita connection of Sol has this form. Now, the vertical field E3 foliates Sol by vertical geodesics, and the sectional curvatures of the vertical plane fields E1, E3, and E2, E3 are equal to -1, while that of the horizontal plane field E1, E2 is equal to 1. The leaves of the first two canonical foliations, X constant and Y constant, are isometric to the hyperbolic plane H2, and these leaves are the only totally geodesic surfaces in Sol. The leaves of the third canonical foliation, Z constant, are isometric to R2 with its usual flat metric and are minimal. This, together with the maximum principle, shows that there are no compact minimal surfaces in Sol. Finally, the curvature tensor of Sol is given by this formula. And now I would also recall some things about surfaces in Sol, about previous results concerning surfaces in Sol. So let us consider sigma, a surface of Sol, and Xi, a normal unit vector field to sigma. Then the Gauss and Weingarten equations of the surface are these. The mean curvature function is defined as the trace of the shape operator, or the second fundamental form, divided by 2. And the mean curvature vector field is equal to F times the unit normal vector field C. Then it's easy to compute the Gaussian curvature of the surface by using the formula of the curvature of the Riemannian curvature of Sol. The Gaussian curvature of the surface is this one, and we'll use it to obtain our next results. So the first result about surfaces in Sol I want to recall is this one about compact embedded CMC surfaces. Is a theorem first proposed by Espinar, Galvez, and Rosenberg in 2009, and its full proof can be found in a paper written by Daniel Hauswirth and Mira in 2010. It says that any compact embedded CMC surface in Sol with the mean curvature greater than 0 is topologically a CMC sphere with the same mean curvature. Now, about CMC spheres, it is well known that in homogeneous three manifolds with isometric group of dimension at least 4, there exists a holomorphic differential, which is either the Hopf differential or the Abresch-Rosenberg one. This differential allows the classification of CMC spheres. So these spheres are either round spheres in space form, this is the Hopf theorem, or rotational spheres when the dimension of the isometric group of the ambient space is equal to 4. This is the Abresch-Rosenberg theorem. Unfortunately, in Sol, there is no similar holomorphic differential. This was proved by Abresch and Rosenberg in 2005. So in order to study CMC spheres in Sol, Daniel and Mira developed a new method that allowed them to classify these CMC surfaces for all possible values of the mean curvature greater than 1 over square root of 3, a result which was completed by Mix for all possible values of the mean curvature greater than 0. So we have this theorem that says that if H is greater than 0, then there is a unique CMC sphere SH in Sol with the mean curvature H. Moreover, this CMC sphere is maximally symmetric, embedded, and has index 1. Other results concerning surfaces in Sol include this theorem by Suam and Tubiana obtained in 2009 that says that there exist only 2 complete totally umbilical surfaces in Sol, and this shows that in particular there is only one complete totally geodesic surface. Then in 2011, Daniel, Mix, and Rosenberg proved the half-space theorem for minimal surfaces in Sol, and a result that we will use later is that obtained by Lopez and Munteanu in 2011, which is the classification of constant angle surfaces obtained by using a local approach rather than a global one. So in the second half of my talk, I will present some new results in SOL. They are obtained earlier this year concerning Simon's type formulas and their applications in this context. So as I said, the shape operator A of a surface in SOL is not a Kodazzi tensor. And since we don't have an Abel-Rosenberg differential in this ambient space, one cannot use the Batista's Kodazzi tensor in order to get a simpler Simon's type equation, for example, by using the general Chen-Yao formula. So we have to work in the standard, say, setting to use the second fundamental form or the shape operator. And even though the computations are quite long, they are straightforward and they lead to a quite complicated formula, which you can see here, for the Laplacian of the squared norm of A. This formula is complicated not only because it's quite long, but it also contains all the vector fields in the canonical frame. So it's quite complicated to work with this formula in the exact form that is written here. So in order to apply the formula in some particular cases, we will have to rewrite some of these terms. But before that, I will give a sketch of the proof. So from the Kodazzi equation, we have this formula. We see that we are very far from the classical Kodazzi property. And then we have the Weizenbock formula for the Laplacian of the square norm of A. And we can see that our goal is to compute this second term in the right-hand side. So in order to do that, we will use the same method as Nomizu and Smith in 1969 and then in 1973. We'll consider this quantity C of X and Y defined in this way. And from the Ricci commutation formula, we have a first property of C given here. Then, if we consider a geodesic frame field around the point P on the surface, and if we introduce this notation for the simplicity of writing, we have this formula. And then from the Kodazzi equation, we can compute C of xy, x, and xy. And we obtain this form where Ti denotes this very long term here. Now, from the Ricci commutation formula, we have that this sum we need to compute has this form. And after some, again, very long but quite straightforward computation using the fact that nabla XA is symmetric and this formula for the curvature, we come to our result. Now, in order to simplify, at least in some cases, that initial formula, we need two divergence formulas that hold for any surface in SOL. So we have this formula and this one. They are just simple and direct computations. And plugging them in the general Simon's formula, we obtain a shorter one, this one, which is quite nice when the surface is also assumed to be CMC. So up until now, all the formulas are valid for any surface in SOL. Now we assume that the surface is CMC, has constant mean curvature, and we obtain this formula. Now, before giving some of the applications of the Simon's type formula, I will show you a slightly modified one. Let's call it an adapted Simon's formula. Adapted because it will also include the angle between the normal vector field and the normal part of E3. So first we have this proposition that gives the Laplacian of the squared inner product between Xi and the normal part of E3. And putting together this formula and the first Simon's type formula, we obtain a second Simon's type formula, which looks like this. Now, in the end of my talk, I'll give some pretty straightforward applications for these two formulas, which are gap and non-existence results for closed surfaces in Sol. So, as we remember, we have no compact minimal surfaces in Sol. So, for a CMC surface in this space, we have f different from 0. The mean curvature function is different from 0. So we have a first result, which says that there are no closed CMC surfaces in Sol such that the squared norm of A satisfy these two inequalities at any point on the surface. So this is a gap theorem, and its proof goes like this. We assume that at each point of the surface we have the two inequalities, and we consider this quantity E, which is given by the Laplacian of the square norm of A from the first Simon's type formula we obtained, and we use the formula of the Gaussian curvature to rewrite E and to see that E is greater or equal than 0. Then we integrate the first Simon's type formula over the surface, and we obtain this result, which shows that A is parallel and E is equal to 0. Since E is equal to 0, we get this value for the square norm of A. We also obtain that E3 has to be tangent and our surface is flat. But if E3 is tangent, we can explicitly write the form of the shape operator, and from that form we obtain that the squared norm of A has to be greater than 4 times f squared, which is not possible because the value obtained for the square norm of A is less than 4f squared. So this is a contradiction. So we have our proof. Now, a similar result, which shows that there are no closed CMC surfaces in Sol such that the Gaussian curvature, the mean curvature, the square norm of A and the mean curvature function satisfy this inequality at any point on the surface. It's worth mentioning that unlike in the proof of the first theorem, where we only had to use the first Simon's type formula, now the first Simon's type formula gives some values for the three terms involved in the inequality, and replacing these values in the second Simon's type formulas, we get the contradiction. Namely, we obtain that f has to be equal to 0, so the surface should be minimal, which is not possible. Finally, we have this more general theorem that says that there are no closed CMC surfaces in Sol satisfying this long inequality that comes from the first Simon's type formula at any point on the surface. Assuming that the squared norm of A is constant, we also have this non-existence result that says that with this supplementary condition, the inequality with changed sign also cannot hold throughout the surface. To prove these two theorems, we need both Simon's type formulas. We use the first one to obtain the exact values of K, the square norm of A, and that of the angle between C and the normal part of E3, and then plugging these values in the second Simon's type formula, we can see that the angles between the unit normal vector field to the surface and the three vectors in the canonical frame have to be simultaneously constant, which cannot happen because of the theorem, the classification theorem for constant angle surfaces obtained by Lopez and Munteanu. So all these results in the last part of the talk can be found in a short paper of mine, which is available on Arxiv. But of course, this work is just a work in progress. I'm quite sure that the Simon's type formulas can be applied to study complete surfaces, for example, in Sol, biharmonic surfaces, biconservative surfaces in Sol. For biconservative surfaces, for example, it's quite easy to see from the terms in the expression of the Laplacian of the square norm of A that it could be quite interesting to study to apply that formula for biconservative surfaces. Perhaps one can show something like biconservative surface has to be CMC, who knows. So it's still work to be done in this field, and I hope that at least some of you are interested in this topic, and perhaps this will be useful to your future work. So that being said, I want to thank you for your attention, and I hope to see you all in real on-site conferences in the near future. See you. Bye.